Today we want to look at partial fraction decomposition, and this is a technique that is very useful in algebra and in calculus and pulling apart rational expressions. So I'll show you the different cases of that and give some examples. So first of all, what we mean by that is here you have a rational expression, 1 over x squared minus x minus 2, and I want to pull it apart so I can use it algebraically where I don't have a quadratic in the denominator. So I have done that here, the 1/3 times 1 over x minus 2 minus x 1 over x plus 1. And you can verify that these are equivalent by getting a common denominator on the right hand side and multiplying in the 1/3, and you should end up with what we have on the left hand side. Now if I started with the right hand side, it wouldn't be that difficult. We do that in algebra all the time. But if I start with the left hand side, how do I move to the right hand side? And so that's what partial fraction decomposition will help us do. And so what you need to understand is you have a rational expression. So we use this technique when we have a rational expression. We'll say that's p of x over q of x, where p and q are polynomials. And the degree of my numerator is less than the degree of my denominator. Alright, so there are several cases, and they all depend upon the factors of your denominator here. So we need a factor q of x in order to do this, and that's a very, very important step. And I'll now show you the different cases. So for case 1, what we need is for our denominator, q of x, to have only unique, so q of x has unique and linear factors. So when you factor the denominator, you only have linear factors and nothing shows up more than once. So as our example here, for example 1, let's take 1 over x minus 2 times x plus 1. Okay, so that's our rational expression. And you see we have two factors here, and they're both linear. Now what needs to happen is when I pull this apart, I want to have something over x minus 2 plus something over x plus 1. That's what I want. And what those things are, we don't know. Okay, so we're going to call those a and b, and those are the things that we're trying to solve for. Alright, now to do this, you have two methods. So method 1 we'll call substitution. And this is based upon the idea that if I get a common denominator here on my left hand side and I set it equal to my right hand side, I should end up with the equation 1 equals a times x plus 1 plus b times x minus 2. Okay, so you can think of it as, again, if I get a common denominator on the left hand side and set it equal to the right hand side, or if I cross multiply both sides of the equation, I'll end up with this equation I have over here on the far left. Okay, so for method 1, what I do is I pick my zeros. In this case, my zeros were from here 2 and -1, and I plug those in for values of x. So for example, here first we let x equal -1 and plug it in, and into what I'm plugging it into is this equation here. Then notice what I end up with is 1 equals a times 0 plus b times -3. Oh, and so instantly we end up with 1 equals -3b, or b is -1/3. Nice. Now if I do the same thing for what I need to plug in this time, 2, I get 1 equals a times 3 plus b times 0. Oh, and so in this case, I easily solve for a, or in other words, a is 1/3. And so I'm done. I have successfully pulled this guy apart in partial fraction decomposition. The second technique is called match terms. So I'll do that here. This is method 2. And I'm calling it matched terms. And so what I want to do this time, so let me look again at this equation. I have 1 equals a times x plus 1 plus b times x minus 2. Alright, so that's the equation I'm considering now. And what I want to do is I want to match the linear terms together and the constant terms together. So for example, what I mean by that, let me write that equation down here for reference. We have 1 equals a times x plus 1 plus b times x minus 2. Alright, now if I consider just my linear terms, I'm going to call them my x's, then I know on the left-hand side of the equation I have 0 for the x's, and on the right-hand side I have 1a and 1b. So I know that a plus b equals 0. If I look at my constants, I'll call them my 1's, then I know I have 1 on the left-hand side, and I have a and a negative 2b in terms of my constants on the right-hand side. So this sets up a system of linear equations that I can solve with various techniques. And from that, I should get the same results, that a is 1/3 and b is negative 1/3. So then my expression, which was 1 over x minus 2 times x plus 1, can now be written as 1/3 over x minus 2 plus negative 1/3 over x plus 1. We can write these in a variety of ways. I think the quickest way to write it would be to factor out the 1/3. And so there we have it. We have successfully pulled this rational expression apart. Okay, for our next case, for case 2, let's consider the case where you have a linear term that has a higher multiplicity. So Q of x has linear roots with multiplicity greater than 1. And my example that I'm going to use for here, so this is example 2. Let's say x over x plus 1 squared times x minus 1. Okay, so this time when I pull this apart, I'm going to have a over x plus 1. The denominator is factored already for me. But I have an x plus 1 squared. So what I need to consider then is to walk up my powers, so to speak. So that's going to be b over x plus 1 squared. If it was cubed, I would have a plus c over x plus 1 cubed, and so on. And then over here I have c over x minus 1 for my other root. From there, you can use the same techniques. And so as a note here, let's put here, you have to march up your exponents, if that makes sense. Okay, now what technique do we want to use to solve this? If you cross multiply, you end up with the equation x equals a times x plus 1 x minus 1 plus b just times x minus 1 and c times x plus 1 squared. Now I believe if I do the substitution method, so I'm going to use method 1, I should be able to take care of most of this. So let's let x equal negative 1 at first. If that's the case, then I'm going to have negative 1 on the left-hand side of my equation. I'm going to have a times 0 plus b times negative 2 plus c times 0. And so lo and behold, I end up with b equaling 1/2. Now if I let x equal positive 1 as my other root, in that case I end up with 1 equals a times 0 plus b times 0 plus c times 4. So then I'll end up with c being 1/4. Now how do I figure out what a should be? Well, I just need to consider method 2. So I'm going to use method 2 on here, and I'm just going to match up my quadratic terms. So that means I have, if I match up my squareds, I have 0 on the right hand side of my equation, and I just have I have a squared, and then I have 1c squared. So I know that a plus c equals 0, and I know that c is 1/4, so c plus a plus 1/4 is 0, which means that a would have to be negative 1/4. And so now I'm able to rewrite my fraction, and that will be, so let's see, we started with x over x plus 1 squared times x minus 1. And now I can rewrite that as negative 1/4 over 1 over x plus 1 plus 1/2 times 1 over x plus 1 squared plus 1/4 over 1 over x minus 1. And there we have it. We have successfully decomposed this rational fraction. Okay, now for my third case, we may have that my denominator, q of x, has an irreducible quadratic. And really this applies for an irreducible term in the denominator period, but we just typically focus on quadratics. The same principles will apply. And you kind of have to be careful. So I'm going to do two examples. Example 4, actually this is example 3, right? For example 3, let's take a look at this guy. So we have x plus 3 over x squared plus 1. Now x squared plus 1 does not factor over the real numbers, so it is irreducible here. And if you're going to try to integrate this thing, for example, you would find that this may look difficult. But actually, it's not too bad. Since I have a linear term in the numerator, I could actually split this up as x over x squared plus 1 plus 3 over x squared plus 1. And so if you were trying to integrate, now you could do our first term, you could integrate as a logarithm. And the second term here, you could integrate using as an inverse tangent example. Okay. Now, so we kind of avoided the problem there. So let's look at one where you can't do that. So here, I'm going to have 1 over x squared plus 1 times x minus 3. All right, now this time I have two factors, and one of them is an irreducible quadratic. So again, I want to split this up as x squared plus 1 over something, or something over x squared plus 1 times plus something over x minus 3. All right, now since this is an irreducible quadratic, that numerator is going to be a linear term. So it's ax plus b. And then that leaves c over x minus 3. Okay, so now when I get my equation that I typically want to reference, I have 1 equals ax plus b times x minus 3 plus c times x squared plus 1. Now the annoying thing about these with the irreducible quadratics is that the elimination method's never going to help you completely, because the whole point of that was that it was irreducible. You're not going to be able to zero that out. So what do we do? Alright, so we have to go to method 2, and just give me a second. Let me write down that equation we're going to reference again. So again, that's 1 equals ax plus b times x minus 3 plus c times x squared plus 1. Okay, now if I use method 2 and I look at first my quadratics, the quadratic terms, I have 0 on the left hand side, and on the right hand side I have an ax squared and I have 1cx squared. If I look at my linear terms, again on the left hand side I have 0, and on the right, if you multiply this out, you get negative 3a plus b, and over here we have no c's that are linear. And then if I look at my constant terms, I'll call them my 1's again. I'll end up with 1 equals negative 3b plus c. So here I have a system of equations, and depending on how this works, you can solve it a variety of ways. What I'm going to notice here is that a equals negative c. And so in doing that, I can replace my equations here as being 0 equals 3c plus b, and 1 equals c minus 3b. Okay, now solving these with systems of linear equations, I'm going to say negative 3 times the second row plus the first, and I'll end up with negative 3 equals 0 times c plus 10b. And that'll allow me to establish that b is negative 3/10. And in a similar way, I get c is 1/10, and so a is negative 1/10. So then, my final decomposition is, so we have 1 over x squared plus 1 times x minus 3 equals, so what do we say for a? We said a was negative 1/10, b was negative 3/10, and c is negative 1/10. So I'm going to go ahead and factor out a 1/10 out of everything. And when I do that, I had my I have x minus 3 over x squared plus 1 minus 1 over x minus 3. And there's my final partial fraction decomposition. Now, if you have multiple irreducible quadratics in the denominator, or quadratics that are irreducible of higher degree, all you do is combine the techniques that we've illustrated through these examples. If you have questions on a particular one, leave it in the comments and I'll try to address it. I hope this is helpful. Partial fractions is a great tool, but it can be confusing at times. And it's always good to have a review in place, and that's what this video is here to serve. Thanks for listening.